Okay, so if you think it's more fun, if they come, we do it like that. We
Okay.
have 1 hour and a half, so should be sufficient. So overall, we have 1 hour and a half.
Okay.
And yeah, so what I can do is if they appear, then I kind of read it loudly to you and then, right? Okay,
Okay. Sounds good.
okay.
Okay, Tim. While people are getting inside the virtual room, thank you very much for accepting being with us and to give us this night's talk. We are all expecting it. I asked Fabio to coordinate the session. Anyway, I welcome everybody else, mostly Brazilian people from the database community. Yeah, we're looking forward to watch your presentation. Fabio, your turn.
Okay, thank you, Sergio. So first of all, like to thank a lot to Tim for accepting and joining us within SBBD and share his thoughts. Today, his talk's gonna be towards learning the algorithms, data structures, and systems. I think this has been a Sigmod tutorial in 2019. And so Tim has given huge contributions on this link between machine learning and databases since his learned index work and many others, which actually is quite prolific and working in different fields. There is a short bio that I would like you to know about. So Tim Kraska is currently an associate professor at MIT at Computer Science and Artificial Intelligence Laboratory and co-director of the Data Science and AI Lab, CSAIL, DSAIL at CSAIL. His research focuses on building systems for machine learning and using exactly so this inverse function machine learning for systems. Before joining MIT, Tim was an assistant professor at Brown University, spent some time in Google Brain at the AMP Lab laboratory at Berkeley. And he got his PhD from ETH in Zurich. He has received many awards. Just to mention a few, he received a P. Sloan Research Fellow in Computer Science and VLDB, a very prestigious VLDB Early Career Research Contribution Award, Early Career Research Achievement Award at Brown University, NSF Career, and so on. I'll bring a quote from his webpage, which I think is very um, expressive of his work. So he goes like, my group aims to dramatically increase the efficiency of data-intensive systems and democratize data science by enabling a broader range of users to unfold the potential of their data through the development of new generation of algorithms and systems. This entails exploring how we can build systems to better support the recent advanced machine learning systems for ML, and how we can leverage machine learning to improve systems, ML for systems. So without further ado, let me pass over the speaker to Tim. Tim, the stage is yours. Thank you very much again to join us at SBBD 2020.
Again, like, thanks for having me. I'm glad that this worked out. And I'm really excited for like this opportunity to give the talk here. I just discussed it with Fabio. So like, given that we are not a huge amount of people, but like still not too small, I think it would be actually fun that we keep it interactive. Meaning, if you have any questions, just ask. And these are actually my favorite types of talks. They're just like, we can rather have a discussion than me just talking for now an hour. This is particularly true for virtual talks like this one, because it's very weird, given that you only see like some names on the screen or maybe a headshot, but no other reactions. So because of that reason, I also removed all my jokes, because it's so weird to do a joke and don't see anybody or hear anybody laugh. So forgive me for that. To exactly just jump in, so there's a current trend of like that the like more and more components inside the database system are actually what we call ML enhanced. And some of them are just like research prototypes now, and some are actually already like you hear at least rumors that they're integrated into production. What I find most surprising is how deep it goes by now. So I like at some point I looked into like, okay, which different components by now in a database system get like ML enhanced. And what you see here is the standard architecture, database architecture by Hellerstein, Stonebraker, and Hamilton from their book. And what we did as the first step was just like we looked into access methods, particularly like on how to enhance index structure through machine learning. Since then, there has been other things like, for example, there's scheduling was more or less at the same time done. Query optimization and query rewrites is like a very active research area right now when machine learning shows a lot of promise. There's plan execution, admission control, log management. Essentially, like every single like box I show here, you can at least find some work that shows on how that actually could be improved using some type of machine learning. So it already goes pretty deep. So the question is like, why is this actually a good thing? And the reason is that we believe that by like using machine learning, we can achieve something which gives you better performance, maybe potentially to reduce costs with less administration, because the algorithm or the component itself can automatically self-adjust to data and workload. And that's the core idea, that you create self-optimizing data structures, algorithms, and systems components which take advantage of a particular instance of an application and a particular user, right? So it's like it self-optimizes to what the data and the workload is. To exploit that, actually, we looked so far at a whole bunch of different components, and like as a first step, we really just took like I think it's like a chapter from a database book, and we looked into like what can we actually do better if we like use machine learning in there to make it self-adjustable to the data and the workload of a particular use case. And the list I have here on the screen right now are just like the things we looked at some point as part of the D-Cell lab at MIT. So all of them, we have at least like one paper written which shows on how you can create something. And as you can see, those are like really the fundamental data structures and algorithms. Some are database specific, like for example, SQL query optimization, but other things like indexing, Bloom filter sorting are really most general purpose algorithms which you can use in any type of system, right? And this just gives you an idea on how deep it goes. So how do you create like a self-optimizing data structure or algorithm? And there are like different ways to do that. The first one, and this has been around probably the longest, is that you configure or synthesize a traditional algorithm using a model. Like particular configuration search has been around for quite some time. This is like you either have like an existing algorithm which is a bunch of parameters, and so normally you need to write a config file. You rely on somebody to set the right parameters. And in the auto case, it's just like essentially you have a model which sets the parameters for you in the best possible way. Right? So just like a way of automating, essentially like figuring out the right configuration of a traditional algorithm. Some work at Harvard actually goes a little bit further. They synthesize traditional algorithms, so they can automatically create like a traditional algorithm using like a model to actually achieve like combinations which were not possible before. The thing is, like those actually have been explored the longest. There are examples of Oracle, like the self-driving database they have. Google has something, Microsoft has something. This is not what we are doing. So we are more interested in the next category, which is just like that we actually combine somehow machine learning directly with an algorithm or data structure to create something new which hasn't been there before. So by more closely embedding it, right? And I have a whole bunch of examples how that potentially looks like. So from the list of like algorithms I showed you before, all these ones are actually like approaches where we embedded machine learning model with an algorithm to create something new. It's not the traditional algorithm anymore. It's not just a model, It's just like a combination of the two, and you have to combine them in a clever way to get like certain benefits. Okay. The ones I show you here now are all CDF-based algorithms, meaning what we do in the end is we learn a model over the data distribution, and then we use this model of the data distribution to create a better algorithm. Right? So this is the core idea behind all of them. It's just a quick recap. I will start with the one which is potentially the most known from all of them, what we did so far, and that's index structures. Just to give you a brief idea, it's also somewhat like one of the little bit easier ones to understand. And then I go over some of the other ones very, very quickly. So this provides you more like an overview without going very deep in any of them. If you want to know more details, I'm happy to shed more. Okay. So for indexing, like I normally compare indexing best to trying to find something in the library. Right? So how do you find something in the library? It's just like the traditional approaches. You go to a catalog. For example, you're looking for the Harry Potter book. There's a catalog of like all the titles of all your books in your library. And then you find the right index card, which tells you where the book is. If you have a really large library, you might have like one of these drawers organized in a full cabinet, and maybe you have a full room of cabinets of that, right? So now finding a Harry Potter book, what you do is like, first you find the right cabinet, then you drill down to the right drawer, and so on until you find actually the index. Nick, this is exactly the same approach than what a B-tree or a normal index structure in a database would do, right? So we have the highest level, which is just like a rough division of all the titles by just like, let's say, the starting letter, and then you drill down further and further until you have the index card in hand, which tells you where the data is in your library, and in the case of a database system, essentially where the data is on disk or in main memory or somewhere else. Okay. However, in the library, there's a different approach to find a book, which is often much, much faster than going through the catalog. And that is, you ask the librarian. Right? There's somebody often there which knows more or less the library. He can probably not tell you exactly at which position in one of the shelves the book is, but he gets close enough. So he can point you directly, hey, there's the book, Harry Potter, probably in the kids section. It's on the second floor or whatever. And then you do a little bit of localized search to just find it in the end, right? You don't need to know the exact book number. It's just like good enough that it points you in the right direction. Right? So he has like in the end, what the librarian has, he has a mental model of where books are in his library, right? And even better, like often he can like have this model and rearrange all the books and adjust the model as well as the books where they are at the same time, so that he better or is more easily to remember what's relevant. And it's like, it makes sense that all the books, for example, in the children's sections about children's books are together. Right? Also, you can adjust to trends. For example, like probably in the summer, nobody is interested in Christmas books, but in the winter that changes, right? So depending on the access patterns what like people want, you can also rearrange what is in the library and make decisions based on that. And this is exactly the same principle we are trying to exploit with the idea of learned indexes. So what we took is just like we took the catalogs we had before and replaced it with the librarian. So the big question for us is just like, if you have a traditional index, can we not also replace it with a model using the same principles in the end? The model predicts roughly where the data is, and then we do a little bit of localized search in order to actually find them. Important here to notice that we are not doing any approximations. On the high level, even a learned index, which uses a model, gives you the exact same semantic guarantees of like the normal index. It's not an approximate structure. And that's important. It's just like it's a plug and play replacement of a traditional B tree, now just using a model. Yeah. So that's the idea behind that. This paper we published in 2018. The idea on how to build the model is actually surprisingly simple. So let's assume we want to build an index on, let's say, the date column here. So I have a bunch of orders, what I want to index as date, so that given a date, I can find all the orders corresponding to that date. So what I do first is now I sort all the orders by date. So this gives you already a hint of one restriction. It's like what we are talking here about is a clustered index, meaning the data has to be sorted by whatever you are indexing. And then if you have all the sorted one, actually finding something in the sorted list is as simple as building a CDF model, taking the probability mass of what we are looking for times the numbers of records we have. So what that actually means is like we are calculating here an offset into the sorted array of all the dates by taking the probability mass of like how many books or like orders have been appeared before this date, which gives me, let's say, oh, they are like 31.25% of the books were there before. If I multiply that then with the total number of orders or books, for example, I have, it gives me an offset, which gives me exactly like somewhere in this list, like where the order should be. And this might be off because this model, this probability might not be perfect. So if you would have the empirical CDF, meaning the exact CDF of all the books we have, then this would be all fine. But if this is just like something which is not perfect, essentially what I get is then an offset. And then I need still in the end to do a little bit of localized search just to find the actual data I'm looking for. Okay. So what we did eventually is now given a key, we have the model which points us somewhere in the index, and then we did a little bit of localized search. And this in total gives us the same semantic guarantees. So the first question is like, what type of model should we use? And the question or the answer for that one is actually surprisingly easy again. It's like whatever works. Right? So in some cases, let's say you are indexing like the primary key column of like some data, often they are auto increments from like some value because they're auto generated. Often a very single linear model might be perfect. Sometimes even the identity function is enough. Right? Whereas like if you have something else like date, it might be a little bit more complex and you need something else. The key things often is that why it works so well is that we tend to use continuous functions rather than discrete ones. So if you think about a B tree, it's also actually B tree is nothing else than building a model just with like discrete values. It's building a decision tree, right? Which is like cut points, split points, but you need like a lot of keys stored in this decision tree to get down to the position estimate. What we are doing often instead is like we use continuous functions, which turn out to be good enough, in particular, very fast to execute. So potential models include everything from neural nets, regression models, piecewise linear functions, and so on. In practice, what we found to work extremely well is what we call the recursive model index. This is inspired by a mixture of experts. So essentially what we do here is that we take a very simple model, let's say a linear model, which we train over the entire data, which gives you position estimates. So this is like a very rough CDF model, right? Which we train over the entire data. Then this gives a prediction, and based on the prediction, we pick another model which was only trained for a subpart of the area, an expert of a certain area in the data distribution. And then we might repeat that process again. Okay? So this is called a mixture of experts because you have one model which predicts roughly an answer. Based on that rough prediction, you pick another model which is now an expert in the sub-range, which makes a better prediction. In the simplest case, this looks like the following. Let's assume we have a two-stage RMI. So we have one model at the top and then an arbitrary number of models on the second layer. And we only use linear models. What it looks like, okay, we train the top model, which is a linear model through the entire data. Based on that linear model, we then get a position estimate and we pick the weights of the next model on the level down here, which are essentially this one that's like the intercept and the slope. And we repeat the process then there, which gives us position estimate. And then we use that position estimate to do some localized search for the actual key. This is like what you see here. This is the entire inference code of the B-tree structure. Right? So it's just like it's two additions, two multiplications in one array lookup. That's it. And that's damn fast. plus like often also very, very smaller than anything else. The other nice thing you can do actually is just like now you can auto-tune this whole thing. For example, you can say this should be a linear model, this should be something polynomial, this should be something else. There was actually a paper led by Ryan at Sigmod this year, which shows on how you auto-tune this whole structure using a combination of different models. The other thing you can actually do with the structure is that you can also replace some pieces with like traditional B trees, which then like, for example, if you see one of these models has a really high error, maybe you should better replace it with something traditional. The nice thing if you do that is that now you can give worst case performance guarantees over the structure because you can guarantee it never is worse than the X, for example, even if you have inserts and other things. So we tried that out. Like initial results we had, there were like a lot of criticisms about that. So recently, actually, we got together with TU Munich and did a whole benchmarking study where we compared our approach using the RMI against like Radix Blind, which is like a different learned index, which is trained top down. Ours is trained bottom up. There has been also another paper called PGM recently from Pisa, University of Pisa, which like uses a relatively similar approach to RS in order to to approximate the function and with that the index, but they have like really nice theoretical guarantees. And what you see here is actually that for all the data workloads, it's just like this is the Pareto frontier, meaning you want to be in this like left corner here, which is like the x-axis is index size, so further to the left means smaller, and lookup time is just like how long it takes you to find the key, and lower means better. And what you see is like with all of them, essentially like the learned structures like dominating all the other ones. Often like 2x in performance, but more importantly, if you take the same performance, the index can be orders of magnitude smaller. And the index size is often what people care a lot about. For example, there soon will be also a publication coming out of Google, which shows you that the index size actually matters a lot if you have a distributed system, right? Because suddenly like more stuff fits into my memory and you might avoid like a second access to disk and other things.
Tim.
Yep.
Can you comment on updates?
Oh yeah, that's my next one. So what about updates, right? So I'm actually not going to talk about updates. The only thing I can tell you, we didn't do them originally. By now there's a lot of work on them. So other groups actually came along, like one work we actually did together with Microsoft called Alex, but they are like other papers out there which extend what we did with updates. The core, let me tell you one thing which is interesting though is, let's assume for the second that the model you build generalizes. What I mean by that is that the data, the new data which comes in, roughly follows the same distribution as the data you already have. In that sense, then in that case, you don't need to retrain the model. There's like in the B-tree case, like it's very likely that you have always still like some reshuffling operation going on. You grow, right? And it's just like, it's not the case that you cannot, you have to rebalance the tree essentially, because the tree is just balanced. It doesn't capture the distribution, where in our case, we capture the distribution and maybe we don't need to do anything even with the model, right? Mm-hmm. So the worst case scenario for us is always the one where like the new data doesn't follow the distribution in any way, right? And like the first question is like, how common is that, right? Mm-hmm. Like it's often not the case that something completely changes from one day to another. And then even on top of that, there's like work like Alex and co, which deal with their scenarios and they try to figure out, okay, how long can we keep the current model versus like completely retraining?
Right.
Yeah.
Thank you.
So insert seems like a downside, but in fact, it might actually be even an advantage, right? Depending on the assumptions of the workload. Okay, so there by now, like this list is by far not complete, unfortunately. I haven't updated it in a while. It's like there has been a lot of follow-up work. Like work which tried directly to improve what we did in arbitrary ways or apply it in different contexts. Like people are playing around with that. More or less, like the takeaway for most of them is just like, oh yeah, it works. What we still need to show is how much it actually matters in practice. There are some cases where we know it matters a lot, but there are others, like, for example, if you increase an index structure from 400 milliseconds, 400 nanoseconds to 200 nanoseconds, it's just like, yeah, the database has so many other operations, probably that advantage is quickly lost, right? So it always depends on the scenario. Because of that, we also started a new thing, which is like CDF-based storage layout optimization, or like also referred to as multidimensional indexing, right? Because we always suspected that we can get better, significant improvements for a given workload if we don't optimize a single index, but take the entirety of all the access paths into account and figure out like the right storage layout as well as the index structure of it at the same time. Okay? The problem, however, is that I can only organize the data in one way, assuming I don't have replication. Okay? So the question is, how do I need to, like, how do I best lay out the data for a given workload in query distribution? And that is what we have been recently exploring. So let's assume for the moment, like I magically figure out based on the workload that date and amount is important for, let's say, orders I have, right? So I have a data warehouse type workload, which have date and amounts, and I want to, like, some queries ask for all the orders above 1 million in a certain date range, right? So also let's for the moment assume like I lay over that the grid, and how big or small the grid cells are again something which I optimize based on the workload. Right? So if like the queries ask for large ranges like month, I make large grids. If they ask for like hours, I make potentially small grids. Okay. So now if I have this grid layout, which is given, I have this dimension. Now I have a storage thing. What I do is like I use the grid layout with a certain traversal function to figure out how to lay it out in storage. And storage can mean here, let's say, main memory, or it can mean disk. So for example, one way to do it is I do column by column. This record goes here, the next 3 records go in these positions, and so on, until everything is laid out. So this is my serialization order. Okay? So now a query comes in. Let's say I'm asking for all the orders with this like order amount in this date range. So how do I efficiently figure out all the records? And here again, we can use models. What we can do is like, we can calculate the probability mass that something happened before that start date. And then I also need to add this like little piece of here, which is just like, oh yeah, it should be the probability above that start date plus like the likelihood that is below the order amount. And based on that, I get a offset again in my serialization order because I know how things are serialized. And I can say scan here. Given that thing here, actually I need several of them. So I might get several points in my serialization order on where to scan. And again, these predictions might be a little bit off. But given that I know on how the data is serialized, I can again do just localized search around it. Okay, so far so clear? So now the question comes down to, how do I build the CDF models? And how do I figure out which dimensions to use, like for the grid structure, which can be 2-dimensional as here, but it could also be like 3, 4, 5, 6-dimensional, right? And like on how big to make the grid cells. And so I have a bunch of like parameters, which is like the CDF models themselves, the dimensions to choose in which order, as well as like the grid cell size. And the CDF one is based on the data. So we built it very similar with an RMI as before. And actually what we do is like we normally assume independence between the different dimensions just to make it easier. That also destroys some of the precision, but it's normally not too bad. And then we pick the cell size, the grid size, as well as the dimensions we want to optimize on based on the workload. Yeah. So given that we tried that approach, this was published this year at SIGMOD. with what's called learned multidimensional indexing. What I show you here is like we have a workload, a data warehouse workload, like using sales. Actually, we got that one from like a local company here. And what we show here is the average query time if you would scan everything. Just like there's no indexing, no layout involved. It's just like it's a column store using full column scans always. Okay. So the next thing is like you could use the clustered column index, right? So like you figure out what's the most important attribute you are filtering by, and you sort everything by that column, right? You can potentially use a Redshift like Z-order encoding. So Redshift has this like really nice paper about like how you can use Z-order encoding for laying out data, and we implemented that as well. And then there are a bunch of like other more traditional multidimensional index structures, right? And this is what Flat does. So in this particular case, we are 3 times better than figuring out the best sort order. However, what's more interesting actually is if we change the workload, actually another technique, the Z-order encoding, is now becoming the best. So this is a performance monitoring workload, which has much more filters at the same time. So that's the reason why Z-order encoding is so good, right? Whereas the clustered column index gets much worse, like an order of magnitude worse. And Flat again is like the best of all of them, which works 3 times better than the next best solution, which changed here in this new context. So it stays at the Pareto frontier, independent of the workload and data distribution, which is normally not the case with all the other approaches, which are designed for a certain scenario, and then somebody has to pick the right thing for the right application and the right data set. And we completely automate that process and achieve even better performance because we create designs which you normally wouldn't do. So these are like the 2 we did. Like recently we have even another paper on that. So this is just to visualize. The KD tree is normally completely workload independent. Flat take the workload into account. Recently we did a new thing called Tsunami, which just like instead of just figuring out one grid over the entire data and everything has to use the same one, Tsunami is actually able to partition different parts of the data in different ways. This is the core idea behind it. For example, it is able to organize the last day in a different way than last year. And before with Flat, that wasn't possible. Everything was organized. It figured out the right organization, but then everything was done in the same grid, meaning it was like it was trying to do the average performance across all the years, including last month, right? Whereas Tsunami is more clever about that. And with Tsunami, actually, we are improving upon Flat again by like almost a factor of 10x across the board, which is then again another factor of 10x better than sometimes the alternative solutions. Right? So like the gains there are pretty significant.
Tim.
Yep.
So how do you design the type of CDF that you apply? Does it matter for you, or how does?
No, like so the CDF, like the models we use here are almost like independent of like what we like. It's like you can use it as an independent component, like what we did for single dimensional indexes. You can use it here. In fact, for Tsunami, it turns out that the CDFs are actually not that important at all. It's much more important how you like figure out the grid size and which dimensions to choose. There's another paper coming, which is like we just submitted it, which also exploits now correlation between the different attributes. So it creates something completely unique based on your workload and the data and the correlations in the data to push the boundaries even further. And in this case, it's more like the optimization process is what really matters rather than the models we use for finding the data. Okay, to give you some other examples, like I think I still have like roughly like a little bit more than 20 minutes left. Like one other one, which I always find cute to show, are Bloom filters. So what is a typical Bloom filter? It just tells you, is this key in my set? It might give you maybe yes. So there might be false positives, but if it says no, it's definitely not in there. So there are no false negatives. In the Learned Index paper, we did a very simple approach to use a model for that. So is this case in my set? We did the classification model for that. So it gives you then a maybe no, maybe yes, right? But then the maybe no's we actually put through a normal Bloom filter again to filter all the mistakes out. And so in total, this new thing gives you again the exact same guarantees with a maybe yes, so it might be false positives, but there are no false negatives. Right? So by doing this over some data sets, like if the model figures out some pattern, you can get huge space improvements using that. If you just have random numbers, it's like your chances of doing anything with your model is like non-existent, right? But if there's something a model can potentially learn, this can do much, much better than a traditional Bloom filter. Also interesting, there has been, like, since we published that again, there has been a lot of follow-up work on this idea. Particularly interesting, I find, like the one Michael Mitzenmacher published like last year, or no, in 2018, and then he did like another work we did now together, partition Bloom filters, this year. It's like, it's almost a counterintuitive idea. So you use first the Bloom filter, then a model, and then a Bloom filter again to give the same guarantees. And you can actually show that under certain conditions, this does much, much better than what we originally had. So like people are creating variants of that where now Bloom filters and models are intertwined with each other. And the partition on Bloom filter improves upon that idea again in a novel way. Okay, another very recent result is like sorting, which I find particularly interesting because sorting algorithms have been around for such a long time. And actually the idea of using sorting came directly from the learned index one again, because like when we published the results, like I think this was a conversation with Thomas Neumann, it's like, yeah, if this works, you can actually sort an O of n. And I said like, yeah, it should be possible, right? Under certain conditions, of course, not always. So the idea behind it is actually pretty simple. You build a model over the CDF of your data, and then you use the CDF to directly place all your unsorted items into the right spot in the sorted array. So if the model here would be the perfect empirical CDF, so if this one would be the perfect empirical CDF, then you could just do one run over the data and put everything directly into the right place. All right? The problem, of course, is it's not the perfect empirical CDF. Right? So like there might be conflicts. Some items might be mapped to the same spot. And in many cases, depending on what type of model you use, there might even be non-monotonic issues, meaning that an item might be misplaced over another item so that the final thing is not even sorted. But even to our surprise, we did an experiment where we assumed a zero-cost perfect CDF model. So what we did for doing that is we generated all the numbers, like all the integer numbers, let's say from 0 to 100 million, right? And now you can use the number itself as the offset into the final sorted order because we have all the numbers, right? So we created all the numbers between 0 and 100 million and then used the number itself as the offset into the final output array. To our surprise, that approach worked, but it wasn't faster even than some traditional algorithms which don't use a model and zero-cost model and don't have the perfect prediction. And the reason for that is that if you do that, you have a lot of random memory access. Like every number here is put into place on the final sorted array, but they might be all over the place. And modern sorting algorithms are highly, highly cache optimized, meaning they do several passes over the data, but they try to do it in a way that most of the stuff stays into like at least L3, right? And so it works much faster than if you have a huge numbers of outputs which have to push to main memory. It's all random memory access. And then, of course, if the model is not perfect, you also have conflicts and other stuff you have to deal with. The first we thought we are screwed.
Would that work also with real numbers? Or it's just...
It also works with real numbers. Normally, we always use real numbers, but like for this Stroman experiment, we used integers only. So we tried different approaches. So in the end, what we had was like an improved learning algorithm. So we train a model on the fly, but then we do several passes over the data so that like we sort into buckets, and the buckets are sized in a way that like the top of a bucket always stays into the cache. So it becomes a variant of radix sort, but just using a model to avoid the typical problems of radix sort, meaning like essentially like what we can do is using our approach, achieve a much higher fan out than a normal radix based one. This is the core trick. So that our fan out normally to distribute it evenly across the buckets, even the skewed data distributions is much better than what radix join in the traditional sense would achieve. Right? And then we repeat the strap of like having the large part into smaller until everything fits into the cache. And there are a bunch of like other smaller optimizations we did, which I just skip over here. These are the final numbers, and this just shows for sorting integers, but we have similar ones for doubles, and we even have done string sorting, so it works for different data sets. What we show here on the y-axis is the sorting rate, so higher means better, right? So as more items we sort per second, whereas on the x-axis is the size of the data set we are sorting. So these numbers here actually include the training time of the model. So it's like we assume that you get the data, we train a model on the fly using a small sample in the beginning, and then we do the sorting using this model we trained on the fly. So the assumption here is, of course, that the data is roughly randomized, because otherwise our trained model in the beginning might be totally skewed, but otherwise there are no other assumptions. Right? And what you see here is like actually that we achieved a 30% improvement over the next best algorithm, which was IS4O, which is a highly optimized memory sorting algorithm, like the best we were able to find, and also outperforms like all the other baselines we were able to get our hands on from radix sort, histogram sort, TIM sort, and other things. Okay, so those are all CDF-based methods. There's another way, and I just want to give you like a really rough idea what we are doing there. It's just like another way to build like a learned component is actually that you use a full model-based approach, meaning that like instead of just like replacing a subcomponent, you replace the entire thing using a model. Yeah, and we did that actually as a first attempt for the query optimizer. So the idea there is that we actually built a full-fledged model to replace the entire query execution, which consists of we first learn from an expert, meaning we first, for example, we bootstrap the system using, let's say, the Postgres optimizer, which gives us some like training data. Then we use that to train a first value model and plant search component, and then we have like the full feedback loop using reinforcement learning, which then gives us some results. And as the back end, we use like a tree convolution in order to get like predictions for a given query plan. So I'm skipping over that like very, very quickly. I'm just telling you, okay, this is a full end-to-end based learning based approach. And the reason why I'm doing that so quickly is I want to get to the next approach, which actually I think is better. Right? So this was like what we did I think it was published last year, I believe. The results of that was very promising. So what you have here is the performance of the optimizer on some benchmark we used compared to Postgres. So one means that the Postgres baseline, so we normalize everything to the Postgres performance, meaning Postgres is as good as Postgres. When you take now Neo, which is our learned optimizer, in the beginning, it's much worse, but then over time, it learns how query optimization should be done and it improves its model. And over time, we are able to outperform Postgres by 15 to 25%, almost 50%, depending on the queries we have. Okay. Interestingly, we also did that for other commercial systems. And also for settings where we didn't have access to the original expert, let's say the Postgres. So keep in mind here in the beginning, we used the Postgres optimizer to bootstrap our system. Right? So like we create a bunch of example data in the beginning, example plans using the Postgres optimizer so that we can shorten the training time. So you need an optimizer to start with. In this case, actually, what we did is we created a different setup. So we compared against Oracle. So one means that the Oracle performance over all the queries. we use the Postgres optimizer on the Oracle execution engine. And this is the green line here, right? So this is like if you would use the Postgres optimizer and force the query plans Postgres produces on Oracle. And as you see, the performance gets actually worse because like Postgres is not designed for the Oracle engine. And it also doesn't have like some of the sophisticated optimization rules Oracle has. Okay. And now we use Neo pre-trained with Postgres, but it never sees the Oracle optimizer before. And what you see then is now the training time gets longer, but like it gets much better than Postgres on Oracle quickly, actually. And then eventually it even gets better than the original Oracle optimizer. Right? And that's like it takes training time, but just like this is an interesting result on its own, right? So we were able to outperform a state-of-the-art query optimization approach using, like this is deep reinforcement learning. The problem with Neo, however, is that like I showed you this like success story before, that it surpasses the Postgres optimizer, is that this little thing here, until it got actually better, took more than a day. Right? So it's a long training time, a lot of resources, and you have to rerun it essentially every single time your schema changes. And it's not just a workload, but also schema changes. So because of that, we created the new optimizer, which is an Oracle-based one, which works a little bit different, but has a much, much faster training time. And we are currently exploiting where we can put it. So Oracle-based predictions normally use a model which predicts something about the future or how something would behave without being completely end-to-end. So how does this new one work? So let's look again at the traditional query optimization pipeline. So what we have is SQL coming in, goes through Pada, goes through traditional query optimizer, which gives me a query plan, which gets executed, gives me some result back at the end. Yeah? We wanted to leverage the traditional query optimizer in the best possible way, but make it adjustable that it learns over time. And we achieved that by creating a feedback loop, which is not there in the original approach. And the way we did that is by creating variants of the traditional query optimizer. So the idea here is that we have the traditional optimizer as it is, but then we also create a variant of the traditional optimizers by, for example, providing a hint set which turns off nested loop joins. Or we provide another hint set which says like, oh yeah, you shouldn't use index nested loop joins or something else, right? No bushy trees, whatever it is. Right? So these are normally the hints a database administrator would provide to the system, right? And we create a bunch of variants like that.
Mm-hmm.
So now we built a model, a prediction model, which takes this variance of the different optimizers and tries to predict on how well they would run. And that's the learning component. Those like are then executed. And then we create a feedback loop so that like if something is really bad compared to the prediction, we learn from it so that next time we pick something better. Right?
And Tim, this last bit you mentioned, so how do you know where to go?
And which one to use? We use a bandit-based approach. So there's an exploitation as well as an exploration phase. So in the beginning, we are more adventurous, we try more things. And as more confident we get, we always pick the best plan, the best prediction. Right? And the TCCN, this is like the tree convolution network again, which is a way to estimate the runtime of a produced query plan. So we have like results for that. So this is like BAO, which is the new approach compared to Postgres. What you see for different workloads, corporate is like real workload we receive from a company, IMDb, Stack. You see actually it improves the performance of it roughly by 50%, like the overall workload time. Interestingly, it also reduces the cost if you would run the whole thing on the cloud, for example. And this includes the cost for all the GPUs and everything you have to rent. So we actually believe this is a pretty reasonable approach. We also compared it to commercial systems. We also see benefits there, which are not as big because their optimizers are normally better, but still substantial, right? And now you have to keep in mind that, like, for example, Oracle roughly spends 5 million a year just for the query optimizer team, right? Whereas this is done by one postdoc. Right. But most interestingly, this approach, actually, the learning time became way down. So essentially from the beginning on, Bao is better than Postgres and keeps up as Neo is in the beginning verse and takes a long time until it catches up. So the main goal we had is like way faster training time. We actually achieved this approach. Yeah. So those are like the four main ways to create learning ahead algorithms. The last one, just for completeness, let me mention that any hybrid is also possible, and you see variants of that popping up. There's just like a lot of excitement right now in the database community to do it. And so far, our focus, as well as the focus of many other people, was like to take a one component, one traditional algorithm, one data structure, and try to optimize that, right? Just like we are very component focused. However, in the longer run, actually, we really believe that we should create an instance optimal system. So what we mean by that is, like, ideally what I want to have is, like, given an application, given a user, I want to give the user the best possible performance he can get and get a customized system just for him. Right. Usually this is not possible, right? Because the complexity of building a database system, if you would do it for one web application after another, it's just like, it's outrageous. Okay? But this is where machine learning come in. It creates ways to help to automatically design and synthesize a system for a single use case and make that still economical, feasible, and like cheap enough. Right? Also interesting is, like, we actually now looking into more the holistic approach, and it turns out that often you make completely different design decisions, right? And that means, like, you give the system more degrees of freedom, because there are more things you can then self-adjust to workload and data distribution. So you come up with designs where you can actually like over configure something for different application and data. Similarly, there's like there are like new opportunities, for example, between components also to share models. For example, the indexing we use for the storage layout, which might be used for cardinality estimation. Right? So there are like new designs we can now explore, and that's essentially our goal with SageDB, which is like a grand effort we really just started to build and to explore on how an instance optimized system should look like. And we will start small and then slowly expand, but like this will bring a lot of these components we have so far developed in separation together. And again, if you bring them together, there are new opportunities. Okay? Just to also for completeness to mention that I gave a pretty database-centric talk here, but like similar trends you also see in like other areas happening, from networking systems, mobile systems, applications. There's like also talk by Johannes Gerke, which gives a good overview about like how other areas are impacted by now machine learning for systems. Okay. There are a lot of opportunities, and some of them we even haven't touched yet. Like, for example, there's this whole idea that in some cases, models can actually change the complexity class of algorithms because they self-adjust to a particular data workload. So we are still trying to figure out what that actually means. There's like huge opportunity for modern hardware, GPUs, FPGAs, and TPUs, which we also haven't touched yet. There are a lot of open challenges, from like, what are the right benchmarks now? Because if you have something like TPCH, like old synthetic data, there's nothing interesting to learn. And in some cases, it's too easy. Like, you get performance improvements, which normally wouldn't be possible in a real world. In some other cases, it's too hard because it's all randomized data and there's nothing you can learn anyway. So like almost any algorithm does it, right? So new benchmarks are needed. There's like the whole question about how to adapt to change, like everything which makes machine learning in general hard. Robustness also partially applies here. Right? So we started to work on some of them, but like, again, this is a pretty new area. There's plenty to do, and I can only encourage people to look into that. Actually, this is like part of the reason why we created a whole lab around that called Data Systems for AI Lab, DCL at CISO, which consists of half systems faculty member and ML members, and big shootout to Google, Microsoft, and Intel for being founding members and sponsors of the lab. And with that, I'm at the end of my talk, and I'm happy to take more questions.
Thanks a lot, Tim. I think the more I see you work, the more enthusiastic I become in this perspectives of machine learning. It's amazing how these models can help and eventually replace most of the algorithms that we've been using for decades in database systems. So maybe I can start with the first question while people write down. Is it okay? Yeah. While people write down their questions and so on. So it seems that you're touching mostly about one of your slides, that is the architecture of the database systems. You show that most of the services or functionality of the database system could be eventually at least complemented or replaced by models. And then, so the first question is this a general pattern? So in the sense that, could that also be true to other systems? And if you go for more like maybe big data systems that already have introduced some of that, like system ML within the optimization, so on. So what are the limits of that to distributed systems? I don't know if that's too big a question for you. And the essence, the question has to be, what is the core property that you should have so that you can apply this method?
Right. So like I would normally say that like you can apply it almost to any system we have, right? It's just like wherever performance or cost or other things matter, I think in general you can use these techniques. Just because like how to best compare it. It's just like I think if you have a traditional system, even without like deeply embedding models, you would probably profit from something which auto-tunes the configuration file for you, right? Otherwise you have to do it manually, but like people are already used to somehow configure a system to get better performance out of it. And in the simplest case, you have a human being doing it, which just takes the workload, sets the right knobs, for example, this page size, this buffer pool size, right? It configures the system for your hardware and your workload you're running it on, right? So the next step is like, you automate that process so that you don't have a human involved anymore, right? And we want to push it even further. We say like, hey, can we not create designs which even allow more customization and adjust even more to the data workload to give you performance which is unprecedented, right? And that's like, so in the end, every system you can apply that to. There's like, in my opinion, there's no real limitation. In some cases, it might not be worthwhile because it's already good enough. And if something is good enough, I change it, right?
Yeah. Do you think, so on the other hand side, so do you think that like linear algebra operators would come into the database and then we could also train models in the database? Do you think that this is
more a question of ML for
tendency?
systems, right? Like this is more like, this is more ML for systems. Like it doesn't make sense to embed modeling and other things in the database. I think there have been approaches to that. MATLAB is like the one which immediately popped to my mind by Joe Hallerstein. Like, I don't think that many of them have been very successful. So you see that it happens, but like all the hardcore data scientists, they normally use other tools outside the database. There might be some sub-communities where it's useful, but I think the larger trend is like, yeah, you have your specialized like frameworks and you get the data out and then back in again. Yeah, I think this is actually almost how it will stay, but like I love to be proven wrong.
Right, yes. Let me see here, we get my chat, how I'm doing. Okay, so I think there are a couple of questions here. So maybe let me see if I can just So Renato, maybe I will turn your can you turn your camera on, and then you can ask directly to Tim your question. I can't see you here. I don't know. Would you like to do that, or Renato? Okay, so yeah. So I'm unmuting your, trying to unmute you. Okay, so now Renato,
Okay, cool.
go ahead.
Thank you. So thank you, team, for the talk. So I have a question regarding you talked about having instance optimized, let's say a query optimizer, right? But what happens if I want to create a new rule for my optimizer? How do I add this to a system that has been already optimized for a particular instance? I mean, do I create again synthetic data and then run it again with a system that has my new rule? And then what should I expect? I mean, yeah, what are your thoughts on this?
Now, that's a very good question. And to be totally frank about it, I don't have a good solution for it yet. So like with Bao, what we actually hope for is like that because the training time until we get better than the traditional optimizer is so fast, you would simply start from scratch, right? You observe the new workload, whatever. Another thing you can do to speed the process up is you can keep some of the past experience, just like keep them around and replay it so that you get at least like bootstrapping behavior there, right? Ideally, what you want to do is transfer learning, right? Take some knowledge you have, transfer it over to the new scenario. We haven't exploited it yet. I think for Bao, it would be relatively easy to do because it's a bandit-based approach, meaning we can say like, oh, keep all the weights, but try only this new one from time to time, right? But it's like, it's in other, for example, Neo, it probably is much harder. Right? What we did do in Bao, which is not shown, is like we actually played around with not like this adding a new rule, but we played around with like how long does it take to adjust when the workload drastically changes.
Okay, it is I think a comment or a question by Sergio. Sergio, you wanna jump in and comment it? Or... Yep.
I was agreeing with Renato former question about the question about what happens if something else happens in the system if you have to restart it, but it's about the same question. It's okay.
Yeah, it's like so I mean, one way is like what we do is like if the training time is so fast, then like it's much easier in many ways anyway. But like I think there's a lot to be done like to improve it even further. And it's just like it's an interesting research area for sure. But the same is also true with any other ML model, by the way. It's like there's not a huge difference, right?
And Tim, what is actually the impact on the search space? How do you deal with that? So now you have the structures, particularly when you show the tree structure where you have eventually different models for different parts of the data and eventually even a B tree and so on.
Yep.
So now we have to decide also on actually, so how does it?
Yeah, there are different, like by now there are different approaches to build learn models. Probably the most complex one is like what the RMI structure I showed you is one of the most complex ones to create in this, like particularly if you auto-tune it with all the model variants, right? It's pretty computer intensive. There are other approaches like the radix spline, which is essentially what it does. It's like it does one pass over the data and creates a learn structure with one pass over it by like using splines fitting and creating an intelligent structure on top. So like again, it depends on what structure you use and how much time you have, and then there are different alternatives by now. There's one other thing for the rule which just came to my mind, which I forgot to mention. One interesting thing we tried in Bao out, it's also in the paper actually, is that you can actually tune the model to not show regressions. So like instead of just saying you want to tune the model, learn everything in a way that it gives you the best possible performance, you do the training in a way that the goal is not to get worse on any query. better, but definitely not worse. And the interesting part of that is, let's assume you have a new rule. The big risk normally is that like some queries get much better and others get much worse. This is the fear of every database provider. It's like introducing something in the query optimization, which makes some customer happy, but others like will suffer, right? And actually the learning-based approach provides you more method, like a more systematic method to avoid that problem, right? So because you can train that you don't digress in performance. So there's again, like there's downsides because the transfer might take longer, but there are also certain upsides like that one.
So Renato, do you want to follow up on your question? You wrote something here. Yep.
So is it okay if I leave like in a few minutes because I have like one?
Yeah, we're just about to finish. Just take this last one.
Okay, great.
Sorry, Tim.
Thank you. Yes, a follow-up on your last comment, actually. So it's about explainability. So you said that for some queries, the queries might be cheaper or better for the user, right? If we would be running this on the cloud and the cloud provider has to charge for a query run to a user, what happens if the query is first it costs, I don't know, $2, and then the next run it costs $1.50. So yeah, how do we explain this to users, right? Or yeah, what are your thoughts on this? Thank you.
So if you do like okay, let me try first a counter argument here. It's like if the standard price would be $2 and suddenly the cloud provider tells you, oh, now it's actually cheaper, we optimized it for you, wouldn't you be happy? Right? So it's like the question is only about expectations, right? It's just like if you say like, it's the same thing as you get like a normal optimizer right now. It gives you $2 and then you get your admin to prove it and he happily reports to you, hey, now I brought it down from running for 2 hours to 10 minutes. Isn't that great? Right? So it depends on what the expectations are. The interesting thing about Bao is actually we make the results explainable. So like one of the deployments modes we have, by the way, Bao is something you can download on GitHub and just try it out with Postgres. It's completely open source, right? So like and we have a Postgres module, which makes it rather easy to try it out even on real world workloads. If anybody wants to do that, please contact me because we would love to get the results for that. But one of the deployments modes we have in Postgres is actually as an advisor, meaning instead of always doing the learned query optimization for you, it looks at the workload and then it tells you, oh, if you would use the following hint set with this query, you actually get a performance boost. Right? And this makes the end decision is then by the admin, right? To use it, but like it's still you get this like you get rid of this manual work normally and database administrator has to do on its own.
Okay, so I'd like to thank very much, Tim, again for your talk and contributing to the community in Brazil. I would just like to take one picture. If everyone likes, the ones that can would turn on their video, I would take a picture of the session and then we can just 1 or 2 minutes for people to.
Tim has to stop sharing his screen.
Oh, I see. Okay, let me.
No, but to me is okay. So now okay. Oops.
Okay.
I have to open. Okay, so now let me. 1, 2, 3. One more. So there are more people. So we had 63 people during the talk. 60, 63, 68.